And what have they made inside? You see the inside? They have put ribs. So you have the walls, and they have put ribs like this. Because the flow is flowing in this direction, and behind one rib, which is like this, you are creating a vortex. You are creating on both sides of the rib. Let's say if this is the rib, you are creating a vortex here and a vortex there. And like this, you increase the Reynolds number, you increase H. And by doing that, you increase also LK, because you have a larger surface, contact surface, between the metal, because the ribs are also made of metal, and the air. Okay? Another solution. This is to make something like this. You see this blade? This blade is composed of two parts. You see, the cooling air is entering through here and is going inside this one. So you have an inner blade and an outer blade. And the air is going inside the inner blade. And the inner blade is perforated with holes. And through these holes, you will blow air at the inner side of the external blade. You are doing that. If you do that, you feel that on the end it's cold. It's exactly the same effect. This is called in English impact cooling or impingement cooling. And this is the technique that is very often mentioned to be the C2. But in fact, the C2, it can be also with the ribs or with the small, let's say, extension that you have inside. The problem with this solution is that you are increasing the weight. If you have a system that is rotating very fast, you have a much heavier blade, and you are pulling on the root here, and you are increasing the centrifugal stresses. So it's hardly applicable to very high rotation engines. And today, engines are rotating faster and faster and faster. So is it something for extremely modern engines? Most probably not, except in the stator. In the stator, this is a very good solution, because it's not rotating, you don't have centrifugal stresses. What you can also do, this is on the inner side here, on the inner side here of the blade. So you have wars, so you have two wars. What are you creating? So this has a certain thickness. You create a surface at the inner side that is like this. You create a surface that is like this. Why? Because the flow of air, the cooling air is flowing here, and you will create here a vortex. You will create here a vortex like this, and this vortex is also increasing the Reynolds number. These are called dimpers. So these small holes that you have in the surface are also improving the situation. Okay? I wanted also to show you that you can have one hole, so the blade is one hole here, or you can have blades with different holes. You see here the holes that are at the tip, because the air is flowing outside. And you have here also different holes at the foot and different holes at the tip. You see? Different cooling channels for convection in this direction. And then there is the other technique, reducing HGLG. What is the technique that is used? We are then doing what is called film cooling. What are we doing? We are perforating the blade with tens and tens of holes. You see some of them here, some of them there. It depends on the system that you have. If you take these blades here, you see that there are holes there. There are holes here also. So you, depending on the situation, you are perforating the blade with holes everywhere, and through the hole, the cooling air, because the base convection is always there. So convection, and then through the holes, you are forming around the blade a film of air. And so that means that the gases that are coming are not impacting directly the metal, they are first impacting the film of air, hot air, or not cold air, that you have between the gas and the blade. So you have a kind of buffer, a kind of external layer that you have put around the blade. Okay? You see that there are different techniques. For example, here we have holes that are tangential, so it depends on the technique that you have. And another way to apply that, it's also shown here. You see that the trailing edge of the blade is also perforated. Because the trailing edge is the place where you have the highest surface to volume ratio, and this is the hottest part. So you need to cool that down very efficiently. And like this, you are decreasing HGLG. Decreasing HGLG. Okay? So doing film cooling, as it is called. And of course, you can combine convection and film, you can combine convection and impingement, and you can combine the three of them. So I don't have a blade where we are combining the three of them here, but here, this blade where you have, of course, convection, where you have impingement, if you would have perforation of the blade, you would have film cooling. But you see that there is a kind of film cooling because the trailing edge is perforated. And these are the techniques that will be used. So HG, LG, and HKLK. Normally LG is not changing. This is mainly HG that is changing. In HKLK, H is changing and L is also changing. You see that when you explain that, you are not speaking about this parameter, you are not speaking about this parameter, you are not speaking about this parameter. We need to introduce another rationale in order to discuss the role of M.K, CPK, and THK. But there is also another parameter that we have not discussed when speaking about HKLK and HGLG, and that is also not directly present here, This is the pressure of the cooling air. What is the pressure of the cooling air? And this is a very dangerous situation if we do not speak about this pressure. Why? Let's consider that this is what you have just behind the combustion chamber. This is just behind the combustion chamber. So this is in an environment that is at a very high pressure. This is almost the highest pressure that you have in the engine. Here around, the gases that are flowing are at very high pressure. So in order to have this air leaving the blade, exiting the blade, this air that is entering here must be at a higher pressure here inside than the pressure there. The cooling air must be, if you are using film cooling, it must be higher than the pressure of the gas. Why do I say that? This is because that means that this air that is flowing here, you need to take it in the compressor. There is no other place in the engine than the compressor. There is no other place in the aircraft than the compressor to take air, because outside the air is at a much too low pressure, the outside air, the ambient air is at a much too low pressure. And so you need to take air in the final stage of the compressor. In order to leave with this air the blade, you must be at a higher pressure than air around. The only air that is at a higher pressure, this is air from the exit of the compressor. And why do I say that it is not directly present here? This is because it's indirectly present here. You see that this is proportional with the pressure. You have a blade that is just behind the combustion chamber. The air that is circulating here must be at a high pressure, so it must come from the exit of the compressor. If it's coming from the exit of the compressor, the TKH at the hub is not low. It is high temperature air, because this is air leaving the compressor. And so you see that the pressure is somewhere present in this TK up, okay? And so this is not going into the right direction, in fact, because you see that you want to apply a technology that is reducing Hg, reducing, in fact, HgLg, but in order to do that, you need to take air at the exit of the compressor, because it must be at a high enough pressure, and by doing that, you have air that is at a high temperature, and this is not a very good cooling air. So we are, let's say, opposing two things in the considerations that we have. And then you have this m dot k. Where is this m dot k so important? I will show you another representation of the problem from the point of view of the complete engine. So we have always said TIT must increase. That leads to an increase of the thrust, and that leads to a decrease of the TSFC. Okay, we have always said that, I don't know how many times. But, how can we increase that in the most efficient way? By cooling. And if I'm doing cooling, that means that m dot k is not equal to 0. And if m dot k is not equal to 0, that means that m dot, let's say in the turbine, is not anymore equal to m dot in the compressor. I'm taking air out of the compressor to cool down the turbine, so in my turbine I have less air than in the compressor. So I'm reducing the amount of air that is delivering torque, power to the shaft. And due to that, what will I have? I will reduce